All right, okay, let's get started. We're going to continue today discussing machine learning on graphs. And today we're going to talk about the problem of links prediction, right? The link prediction. So, overall, like the idea is, of course, to predict if a link is going to appear in the network. There are several scenarios when you might want to do this. So first of all, if we have a dynamic network or network is changing with time. And in fact, most of the networks we deal is in practice in the real world, they are dynamic, right? So social graph is growing with time. You're making new friends. The graph of citation network is growing with time. New papers getting written and cited, et cetera, et cetera, et cetera. And so the idea is giving a snapshot of a network at a certain moment of time, t, predict edges that's going to be added to the network within some time interval. This can work as a sort of just a pure predictor for the links, or you can actually flip this to be a recommendation system, right? In some sense, this prediction can tell you, okay, this is, for example, people you want to meet, and that's sort of how the sort of Facebook or LinkedIn works in terms of recommending your friends, or maybe even a co-author recommendation system where, let's say, for example, it predicts what people you might want to write paper together with, right? So that's one thing. Another application could be link completion. And so the idea is that when we have data, sometimes, well, quite often, some information is missing. And that information can be a link dependency, right? And you can try to see if the structure is consistent all the way across the graph, or if there are some links that could be missing due to, for example, noise in the data, or if you can think about, like, I don't know, forensics, for example, there are missing connection between people, or some, I don't know, monetary transaction that is not listed, but that sort of that is consistent with the rest of the network structure. We can also think about the reliability of the data. Again, for every link, for every edge that exists in the graph, we can try to compute the reliability of that edge, which is like, well, if that is a real edge, or if it's a noise, or maybe some sort of misinformation. So the predictors in this case, what we can predict is, so first of all, it's sort of binary predictor, whether it's going to link exist or not, maybe the probability that the link is going to exist. Then there is a link weight that we can try to predict, or link type. So that's sort of the problem that we want to address. So why is this problem challenging? Well, the reason is the following. Let's say we have a graph, with B vertices and E edges, the way it's shown here. And let's say the dark blue edges do exist, and nothing else. So the number of missing, the graphs that we usually deal with, they're quite sparse, right? And the number of missing edges, right, is a sort of number of possible edges, which is v times v minus 1 over 2, which is approximately v squared, minus number of existing edges. And so number of existing edges is usually quite small compared to the possible number of edges. And so there are lots and lots of possibilities where missing edges could be. And if I just randomly guess, right, the probability to get the correct, to guess the correct location of a missing edge is, approximately order of magnitude of 1 over b squared, where b is the number of nodes. And if we have 100 nodes, it's already a very small number, right? It's already 10 to the minus 4. It's just a random guess. So the baseline in terms of like random guessing the solution is very, very poor. And the reason for that is just because there are so many ways you can actually put an edge in the graph, right? So there again, v squared approximately positions, right? You can put edge in the graph while there is e number of edges, and e is much smaller than that, and so that means you'll have very hard time guessing the right position for an edge. So there are several ways, major ways people solve this problem. So one sort of most popular way is it's the unsupervised way, or it's a ranking algorithm. So what you want to do is we're gonna, for each possible pair, let me try to draw it. So for each possible pair of nodes, for each pair, we can calculate similarity score. And that similarity score will mean that the higher the score, the higher the probability that we will have there. We'll have a node there. So it can be here or here or here, or sort of any other ways. And then after we compute this proximity or similarity score, we're going to sort all pairs based on that score in the decreasing order. And then we'll set up some threshold and select top n pairs sort of above the threshold as possible positions for new links.
Sorry, but you aren't sharing your screen right now.
Oh, the screen stopped sharing. Okay, sorry guys, something broke down. Can you see it now?
Yes, thank you.
Yes.
Right, sorry guys. Okay, so again, so what we can try to do is to try to do link prediction by scoring, by ranking all the edges, and for every link, calculate the probability that this link exists. Then we're going to sort all those pairs of nodes, or all the links, right, in decreasing score order, and then select top n pairs. And for example, we can measure the quality of prediction, say, what's called prediction at top n, where we calculate number of true positives within that predicted set divided by the total number of predictions. So just follow traditional metrics. Now, this seems like an easy way, right, to solve the problem. What are the problem here? I mean, why do we think that there can be an issue here?
Complexity maybe, because for each pair we want to calculate these similarities.
So the main challenge here is that the main challenge would be that we have n squared possible pairs, right? N number of nodes, so n squared possible pairs, and that really leads to the fact that we need to compute this proximity score n squared time, right? And again, if it's a large graph, it's a graph of a size of 100,000 or a million, you just cannot do it. So this is a nice method, but we need to take it with a grain of salt, because it's going to be really hard to go through all the possible pairs, right? If you want to do this scoring. So there might be some sort of ways to select a subset of the most interesting nodes to analyze and then do it within that subset. But it's going to be really hard to do it for the entire graph. But in any case, then the big question is, okay, so how do you actually do this, right? Because yeah, it's one thing to say let's rank the nodes, but then we need to calculate some sort of similarity scores. And there are multiple ways of how we can do it. One way is we can work with their sort of what's called local neighborhood, right? So when we have two nodes and so we have two nodes and we're trying to predict if they're going to be exist an edge between them, right? We can look at the local neighborhood, which means let's look at the neighbors of those two nodes. And I'm going to draw the neighbors and see if there is an overlap, right? So it's a local method because we're looking one step away from the nodes that from the nodes where we want to predict the existence of an edge, right? And so that's why it's local. So the simplest method, the simplest similarity index is really just a number of common neighbors, right? So we have let's say here it's two common neighbors, right? And that's how we can actually calculate this. Now, this method is literally, what can be used, and you probably when you look at the Facebook, it tells you, okay, there is like 3 common friends or 10 common friends or whatever number of common friends. And that's really what it does, right? It just calculates number of common friends for all your neighbors, for all your friends, and then just rank them and gives you like the top number. So again, the easiest one is just number of common friends. Now you can actually calculate Jacquard coefficient, which is the ratio of the number of the common friend of the common friends to the total number of friends. That's one way of doing it. Then there is what's called resource allocation method, where what you do is, and I made a mistake here. It's W, it should be W here, where you look at the number of common neighbors, but then you actually, instead of just calculating this number, you actually calculate one of the inverse. Then there is actually quite surprising metric, which was proposed by Atomic Adder in their paper, and it's just called the Atomic Adder, where instead of just adding it up, you actually take one over logarithm, and surprisingly, this works really well. So this is all somewhat sort of ad hoc ways of calculating the similarity, but it's quite practical.
Can I ask a question? Question, please.
Yes.
What is the idea of the inverse for the similarity? What is the idea behind the inverse here?
Why do we do 1 over n?
Yeah.
Honestly, I don't know. It's actually just words. There's we can try to interpret it saying like, look, if we have say that you have, I would say it's 2 neighborhoods, and there is some sort of overlap, right? And we take 1 over the size of this overlap, right, as a metric. Now, why it works well, I don't know. You can try to look up into the paper. There is no deep math behind it, deep mathematics. People tried, and somehow it worked. I mean, this makes sense to me. This too. These are very surprising to me, but in practice they work.
Okay.
There are actually more of this type of metrics out there. Hold on a second, let me move on to the next one. Onto the next slide. This one is based on this notion of preferential attachment, right? And it actually either you either multiply the degrees of the nodes, or another option, you can add them up. But if you remember, when we model a preferential attachments, the idea is that the nodes of high degree connects to the node of high degree, right? And then and so that actually, this type of preferential attachments, like the first one, actually increases the chances for connectivity among two very high degree nodes, right? So the probability of connecting with two high degree nodes will be higher than the probability of connecting of low degree nodes. And the second one sort of balances out, right? It gives us, it gives us high probability of connecting, of course, if the two node degrees are very high, but and low degree if two nodes are low degree. But it's also kind of for the one, it allows to connect for high degree and low degree. Again, guys, this is all sort of kind of intuitive. There is this hand-waving arguments. It's not a precise science. Then there is clustering coefficient idea. Again, then the notion that if there is a node that has high clustering coefficient value, and there is these two nodes, then we can look at the product of those clustering coefficients. And the reason for that is because clustering coefficient is literally how many triangles the node participates, and the idea that if your friends know each other, then if a bunch of your friends know each other, there's a good chance that the rest of them know each other, so that you're part of this sort of community, well connected. So that's yet one more metric. Now these are all local metrics, right? That's where you look locally. Now nobody says that you need to only look locally, and you might also want to look sort of at further distances. One of the ways to think about this is sort of this negative shortest path. Again, you look at the shortest path in between two nodes, and the shorter it is, well, the more chances that they'll be connected. Then there is this CUT score, and I don't remember if we discussed that the score before or not when we talked about the centrality metrics. But here the idea also is that you calculate the shortest path, but you don't only calculate the shortest path in between two nodes. You actually add it up with a coefficient, and when this coefficient is less than 1, you can actually calculate the sum. And it's going to be, it's going to converge, and there is a way, there is almost a formula you can write. So the idea again that you put a weight on the importance of the shortest path when you have one node, second node, third node, I don't know, fourth node, right? Then there is still a similarity between those nodes, but you calculate depending on how far, how many steps you need to take to reach that node. It adds into the sum with some coefficient that decreases the further paths, the longer paths. Then there is this page rank, and it's called personalized or rooted page rank. Again, you can actually calculate for every node. You can calculate a page rank score rooted at that node. You remember when we did the page rank, there was this teleportation coefficient and a teleportation, and so you can teleport to a particular node, and that's that's very special node where you always teleport in the page rank motion. It's called root, or it's called rooted page rank, and then it's a selected node because it's sort of rooted node, and then you calculate page rank score for all other nodes with respect to this guy, and then that measures your similarity with this guy with all other nodes. So pretty much anything that allows you to come up with different metrics, how similar nodes are, you can use here. Then there are more indices. If you remember, we talked about random walk before, and for example, there's a metric, and I believe we also briefly discussed it previously, which is called the heating time, or literally it's the number of steps before, so the length of the random walk before you reach a particular node. And you can think about this as sort of actual physical random walk, where you you know, sort of simulated the random walk and just calculate number of steps, or you go through the formulas, or you can think about commute time here. Commute time is just the notion, the idea of symmetrizing this, and it's random walk from I to j and j from I, or you can actually sort of normalize it, and normalizing means you calculate the probability of node being in a particular, if you have a stable distribution in the Markov chain over all nodes, and you have this stable probabilities, you can actually use that to renormalize this commute time. So there's like the entire bunch of theoretical approaches how you can use random walk to measure those distances. Again, the idea, if the nodes are very far from each other, of course, it will take a long time for random walk to get there. And if there are multiple ways, you know, random walk can get lost, etc., etc. But if the nodes are next to each other, or if they're, let's say, in one cluster, which is well connected, then, you know, random walk most likely will get from one node to another in a small number of steps. And again, if those two nodes belong to the same cluster, there's a high chance that they're also connected. Yet more metrics. There is similarity rank. I think we looked at this metric also when we talked about centrality metrics. The notion that, you know, two nodes are similar based on their neighborhood, and for any two nodes, you look up at their neighbors, and for each of the neighbors, you measure similarity between them, and then you solve this system of equations where the similarity between two nodes is measured based on the similarity in between their neighbors, whether they're connected or not, right? So similarity, say, in here, between those two nodes is calculated through the similarity in between, say, these nodes, this nodes, this and this node, this and this node, and so on, right? So you solve that system of equations, and that will allow you to calculate similarity between pairs of nodes, and then you can use it, you know, to predict links. Again, notice that for everything we do, there is always this two indices, I and j, and so this is a quadratic problem, right? Because there's, you know, n squared number of computations you need to do, and if for each of those you need to solve this type of a problem, that's becoming, well, it's computationally very, very challenging. Let's put it that way. Finally, there is this idea that if two nodes belongs to a cluster or to a community, then that's definitely increases the chance that they are connected, right? So now we're talking not only about the fact that, you know, two nodes have some number of common neighbors, but it's also how those neighbors are connected among each other in between themselves. And so if they form a cluster, there's a high chance that those two nodes can also be connected. And then we look here at the neighbors, at the nodes that are sitting on the you know, intersection of the nearest neighbors of two nodes, and then we see if they belong to the clusters that has been determined or not. And you know, again, there are different variations of this idea where you look again now, instead of just looking at that value, we look common neighbors with community information. So we look at the number of common neighbors, plus there is some community function that increases for each community. It increases the number of nodes there, or the metric value. Then there is a sort of resource allocation approach, and resource allocation, remember, it's when we divide. That's that idea, the evolution of that idea, where instead of just adding things up, you divide by, you put this one over the number. So all these things gives you score, right? And you can literally, rank all the nodes by one of those scores, or you can rank them, by several scores, rank and re-rank. And that's sort of the most sort of straightforward way of dealing with this with link prediction. Now, if you think in terms of machine learning, by now you should kind of think that, look, these are all different metrics, right? And they all give us similarity score in between pairs of nodes. Why can't we just combine them? And in fact, yes, you can combine them. You can, either do some very simple things, or you can actually formulate this as a machine learning problem, either regression or classification, and think about each of the scores as a feature, right? And so you build a feature vector where every element is a score, and then just set it up as a machine learning problem. And we're going to talk about it a little bit more in a minute. Now, there are a very different also way of thinking about link prediction that has become quite popular. What I'm showing here, this is just one of the examples of how you can do this. The so-called low rank approximations. In other terminology, sort of more of today's terminology, people like to talk about embeddings. But the idea is actually here that the idea is, lies in this truncated SVDs, single value decomposition method. And in fact, it was sort of the first method of like dimensionality reduction method that people used, and then they start doing other things. And so the idea is the following, that when you take your, let's say, adjacency matrix, right? An adjacency matrix has tons of zeros, right, where there is no connections. And I'm just drawing it randomly here, more or less. And then there are ones, and there are ones that put ones on the diagonal, and then there were ones when there are connections, right? So the idea is that you can decompose this matrix, you can factor it out, and that's why it's called matrix factorization also. Single value decomposition is one of the ways to factor the matrix out, which means split it into the three matrices that can be combined back into the original matrix if just taken as is. Or, there are ways to split the matrix, into two matrices or into three matrices. Single value decomposition does three, such that again, when you multiply them through, you get the original matrix. Now, and here is what it says, right? Your original matrix, I should put here A, right? Your original matrix is a dot product, is a product of these three matrices. But what you can do is, instead of actually, multiplying all the way through, what you can do is you can take what this S matrix or diagonal matrix, and you can actually say zero out some number of coefficients here. Now, the S matrix has this nice property that the singular values, they are sorted and they're in decreasing order. And what you can do is you can say, okay, look, I'm not going to use all the values here. I'm going to use just some of them. Now, this can be interpreted as taking these vectors and projecting them onto the subspace. And the number of non-zeros that you will keep will be the size of that subspace. All right. So if I can take any data and project it on, sort of any dimensional subspace less than it was originally, if I want to project on the two-dimensional subspace, then here it's going to have only, two columns, and this matrix will be 2 by 2, and here I'll have only 2 rows. Now, if I do that, and that's called low rank approximation, if I do this, when I multiply back those truncated matrices, I will not get original matrix. It's not going to happen. because when I do this, I lose some information. Instead of that, I'll get some approximation to this matrix. And so, if I do this multiplication, and I'll just show you the result here, what's going to happen in many places where you have zeros, now you're going to have some values. They're not going to be zeros or ones anymore, but they're going to be some values, some numbers. And then you can actually interpret those numbers, select the threshold, and interpret those numbers as new links or new edges that appear in your graph. And this method actually is quite popular, for example, in recommender systems, because your matrix, your adjacency matrix, can be thought of, for example, people, using some products. Let's say rows will be people, and users, right? And rows will be products, and non-zero means people using those products. So it's bipartite graph. And doing this type of low rank approximation fills in that matrix with non-zero values that you can interpret as people trying to buy, other products, and that can work as a can be interpreted as predicting new links in the graph. Now, the problem here is also not very clear, sort of why and how this works, right, from the sort of deeper perspective. Plus, to work on this, you actually need to take your entire matrix, which is entire graph, and if graph is very large, that's pretty hard. But again, like different versions of these methods are very popular today. The simplest low rank approximation is called truncated SVD, single value decomposition. There are like, but then there is like alternative least squares, then non-negative matrix factorization. I mean, there are like lots of ways of factorizing matrix such a way that you'll fill in some of the zeros with non-zeros that could be interpreted as as links appearing into the system. So here you actually take a graph, you look at the matrix, you fill in non-zeros, then you go back to graph interpretation. Does this make some sense? All right.
Yes.
Okay. All right. So that's sort of another way of predicting, edges, predicting links on the graph. Now, moving ahead, just for comparison purposes, if we look at the scoring methods, like stepping back for a second and looking at the scoring prediction, and the method we have previously discussed, this atomic adder, weighted, the cut method, the common neighbors, this is a low rank in a product, which we just discussed. Here it is. Common neighbors, rooted page rank, Jacquard, similarity rank, graph distance, hitting time. And this is relative performance ratio versus random predictions. And this is a random prediction. So it says at 1, as we said, random predictions are very hard. They work really poorly. And this has been calculated over 5 data sets. And if you notice, surprisingly, the best predictor, the best single predictor, if we just look at one predictor, is this atomic adder thing, which was, and now I'm going to go back, remind you what that is. There's this surprising metric that you asked me about, right? Well, surprisingly, this works as a single metric for prediction, for scoring, predicts that the two nodes can be connected. It actually works the best, right, in those experiments, which is quite surprising. So here are those metrics, right? And then there are others. So Jacquard coefficient, well, works better, but works okay, but again, this atomic adder, by whatever reason, the best. And this is the same picture where we use as a baseline, we show common neighbor predictor. Common neighbor is just number of common neighbors, And so in fact, common neighbor is actually a pretty good predictor. It's better than all the random walks, the sort of better than graph distance, this complicated similarity rank. It's surprisingly worse than atomic adder, but it's pretty decent. And so one of the reasons Facebook, LinkedIn, and other social networks use this is just simply because it works pretty well and on social networks, and it's very, very easy and cheap to compute. But let's say we want to go into more precision, right? And let's say it's not necessarily social networks. Remember, this number of closest neighbors work as a predictor in social networks. And the reason it works well as a predictor in social networks, and the reason is being, social networks, there are lots and lots of triangles. And I mean, this notion of, there's a good chance that two of your friends know each other is actually, based on this, and this idea based on that notion, and that works really well in social networks. So that's why that metric is so powerful in social networks. But if you look at other networks, not necessarily social networks, where it's biological networks, protein network, whatever, it might not be the best. So if we go back to sort of more standardized thing, and we look at classification problem, right? With classification problem, if we think about this as a classification, let's say we want to predict the existence or non-existence of a link between two nodes. It could be a binary predictor, 0, 1, or it can be probability, some score, some regression that the link exists. Now the challenge here, of course, is if you want to evaluate all of the nodes, you have to go again through all those n-squared pairs, or you need to select subset where you deal with. But also, as a machine learning problem, the challenge is that that we have a very, very imbalanced class distribution, right? Because number of positive examples, the number of existing edges, are very small, and but at the same time, the number of negative examples, right, the missing edges, those they go quadratically with the number of nodes. Number of positive grows linearly, right? And so that creates very unbalanced distribution. And the larger the graph, the bigger this imbalance is. Now, from the machine learning perspective, why is this a problem? Why is this imbalanced class distribution is a problem for classification algorithms? Did you guys have a machine learning course? Oh, I bet you did. Look, the problem is that when you have high imbalance classes, what algorithm learns is to always predict the dominating class, because then it will by default makes less mistakes, and so any loss function will perform better. And so when you have such high imbalance in between classes, the best performance from the point of view of algorithm is that always predict that there is no link, and that will give you if there's imbalance 90% or 95% imbalance, then it will give you that quality without actually doing anything. And so the challenge in this type of algorithms is how to actually make it work with imbalanced classes.
Yes, we can choose a matrix which is suitable for such imbalanced cases, like AUC maybe, area under.
Yeah, so you can actually, so there are a couple things you can actually try to do, try to adjust the metric, putting much more weight on one of the classes, right? Then you also do subsampling, obviously, to try to balance out classes. So there are ways of dealing with imbalanced problems. But again, this is, and I mean, a lot of problems in the real world are imbalanced. But what I'm saying is, it's a challenge, and you need to sort of pay additional attention to this, because you're trading on imbalanced class. So, and here it just demonstrates you the ratio, and this is shown on a, just on a database with co-authors and collaborations. You know, it shows you like the actual number of collaborations, right? And collaborations, the actual edges, and the possible number of collaborations. And notice that the scale and possible number of collaborations is just number of authors in the database squared, and actual number of collaborations, it's, you know, how many papers has published together. So you know, the ratio, it gives you here the ratio, actual collaborations divided by possible collaborations. You see that imbalance is, what is this, you know, 10,000, you know, 100,000. So it's huge. So what do we do? Well, you know, so first of all, we agree that it's imbalanced, so we'll have to take care of that when we actually train the models. But overall, yes, we need to generate features, we need to do model training, and then of course we need to test. Now, the feature-wise, yes, there is this proximity features that pretty much you can take all those, you know, number of neighbors, number of common neighbors, and add, you know, Adenic Adler. I mean, pretty much any of those features that we, you know, discussed before. I mean, any of those metrics, and use them as features. We can also build some other features, some aggregated features from them. So it's literally anything you would normally do in machine learning. But you can also, if it is, if it's not just a pure sort of structure, but you also have some information in the nodes, you can actually also use some proximity features based on the node content, for example. So we take network, right? We build feature vectors, some of them based on the structure. Some of the features can be based on the content of the nodes. And then, you know, we solve the prediction problem. Now, how do we set it up, the problem? Well, we actually need to take a graph, and we need to hide some of the existing nodes, right? I'm sorry, some of the existing edges, and try to predict them. At the same time, and because those existing edges will be, you know, positive examples. At the same time, we need to take, you know, some number of negative, empty, missing edges, and consider them as negative examples. That's where you can actually think about this oversampling, undersampling. So, for example, where instead of actually going through all the possible negative examples, all the possible missing edges, you just take some sample here, right? And then you need to decide, of course, how many of sort of positive edges you need to hide trying to predict. I mean, how many of existing edges you need to hide trying to predict them, since they're positive examples. And of course, when we do this, again, you know, it's classical machine learning problem. You can think about precision recall. But, you know, precision recall, the challenge with precision recall is that, you know, for example, precision does depend on the class balance. And so it's better to look at, you know, true positive rate, false positive rate, you know, ROC curve. And this is an example from one of the papers. There are two networks the authors worked in with. One is the phone network. The other is condensed materials network. ConMat is a network for condensed matter collaboration. This is for physics papers. Now, what's interesting to notice here is, you know, the traditional ROC curve. I'm sure you have seen this before, right? Diagonal means you pretty much have a random algorithm. Everything above the diagonal is good, below the diagonal is bad. And the further you go above the diagonal, sort of the better. And I think it's quite entertaining. Notice that preferential attachment, for example, for this graph is actually making, you know, it's wrong, while at the same time for other graph, it's actually a pretty good predictor. And the reason for that is probably, you know, this graph, and this graph is a collaboration graph, and this graph is a phone call graph. In collaboration graph, the graph itself grows based on somewhat on preferential attachment model, because again, CONT-MET, these are collaborations in science, in scientific papers, and somebody who is becoming more and more popular as a collaborator, the more people goes to him, and that's exactly the notion behind the preferential attachment. And so here it actually describes things well. In the phone calls, if you're getting more calls, doesn't mean getting more calls will cause more people call you, right? And so here this metric is just failing. But surprisingly, again, the atomic adder works really well. Here it is, right? And I don't see it here. And then this HPLP, this is the author's way of solving through through supervised learning, right? So it does the best, obviously, combining things together. Interesting, I just noticed that there is no actual ROC, there is no value under the curve shown here. But looking at this graph, it's probably I would guess somewhere 0.7. I don't know. So it's decent. It's decent. You can guys look up in the paper. Now, one last thing I want to mention, and that's quite important, and that's sort of always important in this type of problems, in the time of problems that involve time. So remember when we discussed the application for link prediction. One application obviously is like missing links, etc., etc. But then the most interesting application is trying to predict the link formation in some moment of time, right? So in the next moment of time. And the challenge here is to do everything sort of nicely and correctly. So let's see. We need to first of all have a test and train frames, right? And obviously, we need to train on the data on the frame that is in time-wise past the test, right? I'm sorry, test past the train, right? So first, if we take a time axis, you always, train on something and then test it on the future data, right? You don't want to sort of train or test, in reverse, right, before the train data. But here is an additional challenge, is because both features and labels, they come from the same graph. And so the idea with time evolving graph is the following. Let's say we are at the moment of time t. So what we're going to do is the following. We're going to use links that existed on the previous moment of time, t-1, for the features. And we use new links that appears at time t as labels. So everything that appeared, all the links that has been formed before time t, so including times t-1, they are this backbone of the graph, and they used as the features. So all these connections are used as the features. For example, we take A, B, two nodes, they have two common neighbors. So that's what existed. Now, at the time t, let's say the edge has been formed in between them. And so then it goes into the label for those two guys. Nodes C and D, here they are. They have one common neighbor, so the feature is 1. And at the moment of time t, there is no edge appearing here, so there is nothing here, no edge. And so the label is negative. We can take any two other nodes, since in this particular picture, it's only one edge that appeared at that moment of time. It's in between A and B. There's going to be only one label Y, or yes, or positive. But you can pick up any other two nodes and calculate, for example, labels for this connection in between those two nodes, and the label will be negative. et cetera, et cetera, et cetera. So that's what you do when you train the network. When you test, you actually do exactly the same thing, but you need to go, forward with several time steps. You can go with, literally one time step if you want to, and just repeat the same process. Or, if you want to be, so in that, if I do that, my picture for training and test set will look like that. Or, it will be probably better, kosher, if you go into more time steps so you don't even overlap them. But that really depends on how many time steps you have in your data. So that's where you need to be really careful, because again, otherwise you can get what's called signal leakage, and your algorithm will not work well. Okay, so that's training and testing when you have evolving networks. To be fair, there are actually many more methods how you can predict links. Then there is this hierarchical models, assuming that the graph is hierarchical and tries to use this hierarchy, try to uncover hierarchy and use it to predict network, to predict edges. It is different Markov random field models. There are Bayesian networks. So lots and lots of approaches, but again, I think the most practical is really either by literally calculating those features and ranking things, or going through this sort of classical machine learning approaches. Here is a bunch of references. Now, on the next lectures, we're actually going to talk more about graph neural networks, and we're going to talk about embedding of the nodes into low-dimensional space using sort of various approaches. And then this link prediction problem can be formulated using those embeddings, right? That's going to be a slightly different way of doing it. There, if, for example, you get two nodes projected on this low-dimensional space next to each other, well, there is a high chance that they're connected in the real world by an edge, right? So that will be the idea for embeddings. When we talk about it, we'll come back also for a moment to that SVD notion and realize that that's sort of one of the projections, one of the simple embeddings. All right, with that, we're done with this lecture. Any questions? All right, guys, well, thank you very much. And then I'll see you on the next lecture. Thanks.